Oxidation number. What is oxidation number? It is a relative charge which appears on an atom in combined state. For example, when we write H2O, hydrogen here is +1. If it is 2 hydrogen atoms, these are going to be +2 total charge, 2 positive. Oxygen, let us suppose, is X. The 2 positive plus X, and as this molecule is neutral, 2 plus X is equal to 0. X comes out to be -2. So we can see oxidation number of oxygen here is -2. That means in this compound, hydrogen is +1, 2 hydrogen atoms +2. Therefore, oxygen is -2. So we can say oxidation number of oxygen is -2. Now this is oxidation number, and there are some rules, some points are there. Those are to be learned by heart for calculating oxidation number. If we want to calculate oxidation number, some rules, some points we must remember, and those points are: first point we have is oxidation number of element in their elementary state. In their elementary state is taken as 0. For example, if it is written sodium, now it is not in a combined state, it is elementary state of sodium, we can say oxidation number is 0. Zinc, 0. Cl2. Now chlorine, elementary state of chlorine is Cl2, as gaseous Cl2 form bimolecular homoatomic, oxidation number 0. If it is bromine, Br2, oxidation number 0. Iodine, oxidation number again 0. When we write P4, oxidation number 0. S8, 0. It means if elements are written in their elementary state, their oxidation number is taken to be 0, and this is the first rule we must remember. Second point, fixed oxidation numbers. Fixed oxidation numbers of few elements. In our periodic table, we are having few elements with fixed oxidation number. That means their oxidation number do not vary in their compounds. It's always constant, always same. And these elements we have to learn. Element of group 1, that is lithium, sodium, potassium, rubidium and cesium. All these are going to be +1 in their combined state. When these elements are in their compounds, their oxidation number is always +1. Next here, group 2, beryllium, magnesium, calcium, strontium, barium, always +2. It means group 1 +1, group 2 +2. Fixed oxidation numbers are there. Aluminium, always +3. If it is written zinc, fixed oxidation state of +2. cadmium plus 2 and fluorine minus 1. These are important elements. Those are going to have a fixed oxidation number, no change in any of their compounds. Thus we can say these elements we must remember, we must learn. It's going to be lithium, sodium, potassium, rubidium, cesium. Then we are having group 2. Group 2 is going to be beryllium, magnesium, calcium, strontium, barium. Then it is aluminium 3 positive, zinc 2 positive, cadmium 2 positive and F1 negative. These are fixed oxidation numbers. Right? Learn again. Group 1 all are having +1 oxidation state. Group 2 oxidation number is always +2. Aluminium +3. So, your zinc +2. Cadmium +2. And finally fluorine with negative charge, 1 negative. Next point. After knowing fixed oxidation number, we must know hydrogen. Hydrogen is an element which can show H plus 1, H minus 1, and if it is H2, then it is 0. It means hydrogen in elementary state is 0, but can be +1 or can be -1 also. Hydrogen is +1 when bonded to some non-metal. If hydrogen is bonded to a non-metal, it's going to be +1. Hydrogen -1 when it is bonded to metal. Metal we can say electropositive element, and non-metal it is electronegative element. So if hydrogen is bonded to an element which is more electropositive than hydrogen, the hydrogen will become negative. And if hydrogen is bonded to an element which is more electronegative than hydrogen, then it will become positive. It means hydrogen can show a variation. Hydrogen can show a variable oxidation state. With metals it is +(-1) and with non-metals it is +1. For example, see some examples of hydrogen in which it can act as +1 or -1. For example, if it is written ammonia, here it is nitrogen X. Hydrogen here is bonded to a non-metal. When it is bonded to a non-metal, it's going to be +3 because 3 hydrogens are there, equal to 0. X comes out to be -3. If it is H2S, sulfur here is X, hydrogen is +2 because again sulfur is a non-metal. Total oxidation number of these two elements is 0. The X comes out to be -2. But if we write CaH2, now calcium is X. Hydrogen is now -1 because calcium is a metal. So calcium is bonded to hydrogen. X -2 is equal to 0. X comes out to be +2. If we write lithium, aluminium, hydride, in this compound 2 metals are there and 1 hydrogen. It means hydrogen here should be -1. We have lithium +1, aluminium +3, hydrogen minus 4 is equal to 0. It means correct answer hydrogen minus 1. So we are having hydrogen, a variable oxidation state showing element. This element has tendency to show +1 charge, -1 charge as well as 0 charge. When we see H2 gaseous or H2 in elementary state of hydrogen, so we can say it is 0. When hydrogen is bonded to a non-metal, it's going to be +1, and it is bonded to a metal, it's going to be -1. Right? This is all about your hydrogen. First rule, elements are having elementary state and oxidation number 0. Second rule, some fixed oxidation numbers are there, and these fixed oxidation numbers are group 1 always +1, group 2 always +2. Then we are having after group 1, group 2, there is zinc +2, cadmium +2 and fluorine -1, aluminium +3. Third rule we have done hydrogen. Hydrogen can be -1, +1 or 0. If we say hydrogen +1, then it is bonded to non-metal. Hydrogen -1 means bonded to a metal, and we can calculate this oxidation number as shown in these 4 examples. Now next rule. After this hydrogen, we are having next important element in oxidation number is oxygen. When it is about oxygen, oxygen can show -2, that means oxides, -1, peroxides, -0.5, superoxides, 0, elementary state. +1 with fluorine. Example of +1 compound is O2F2. When we write O2F2, here fluorine is -1, so we have 2x for oxygen plus -1 into 2, that is 2 fluorine atoms. It is equal to 0. 2x is equal to +2. X comes out to be +1. Right? Oxygen can be +2 also. Example, OF2. It is x minus 2 is equal to 0. X comes out to be +2. It means oxygen can show oxidation number from -2 to +2. There is one compound of oxygen that is named as O2PtF6, platinum hexafluoride with dioxygen. In this compound, platinum hexafluoride is -1 and O2 is +1. It means 2x is equal to +1, that is oxygen's charge. X comes out to be +1/2. It means variations in oxygen are large in number. We are having -2, -1, -0.5, 0, +1 and +2. Even +0.5 is also possible in one compound. Here we have O2F2 is the only compound where +1 is existing. This is the only compound O2F2 in which we have +1, and this is again only compound where we have +2. It means positive oxidation state of oxygen is going to be rare. Very rarely, or we can say rarely, it is possible to have +1, +2. Only 3 examples of positive oxidation state I have written, and these 3 examples are the examples in which oxygen is positive. Otherwise, generally 99% times it is going to be a negative oxidation state. Okay. Now we have oxides, peroxides and superoxides. How we came to know that this is oxide, peroxide and superoxide? So for this information, we will discuss some examples. Let's start with some examples. I write these examples as, when I write NaH, CaH2, the sodium is +1, hydrogen -1, calcium +1, +2, hydrogen -1. It means alkali metals and alkaline earth metal, that is group 1 and group 2. These are going to have a fixed oxidation number, and we have calculated hydrogen. Same rule we can use for oxygen. We will take fixed oxidation number of one element like alkali, alkaline earth metals and oxygen. Let's see. If it is written sodium oxide, Na2, sodium is always +1. It is 2 into +1 plus X is equal to 0. X comes out to be -2. It means this compound should be named as sodium oxide because oxygen here is -2. But if I write Na2O2, sodium is +1, it is 2 positive now, plus 2x is equal to 0, x comes out to be -1. When it is coming to be -1, it means oxygen here is -1. This compound is now named as sodium peroxide. Sodium oxide and sodium peroxide. It means if sodium is known to us, we can know that the compound is oxide or peroxide. Some other examples, let's see. If I write K2O, K2O2, KO2, H2O2, CaO, CaO2, BeO, MgO. If these compounds are written, one more example we can write Al2O3. In these compounds we can identify whether these are oxides or superoxides or peroxides. And it is to be remembered, superoxides are possible or are existing in group 1 elements only: potassium, rubidium and cesium. These 3 elements can form superoxides. It means concept superoxide is very rare, and you just remember 3 elements, 3 superoxides are there. One is potassium superoxide, rubidium superoxide and cesium superoxide. It means now major confusion is between oxides and peroxides. Let's check. Here potassium is +1, oxygen X is 0, X comes out to be -2. It means it is potassium oxide. Next, potassium 2 positive, plus 2x is equal to 0. Now x comes out to be minus 1. This is potassium peroxide. Next, x, so it's 1 plus 2x is equal to 0. X comes out to be minus half. And now this is a superoxide, potassium superoxide. Formula of 3 superoxides is KO2, RbO2 and CsO2. These 3 superoxides you must remember, only 3 in the periodic table. In complete periodic table, there are only 3 superoxides existing. Now calculate for this oxygen. 2 plus 2x is equal to 0. X comes out to be minus 1. It is hydrogen peroxide. Right? Now calculate oxidation state of oxygen in the 4 compounds left with us, 5 compounds. Calculate oxidation number of oxygen in these 5 compounds. Should we discuss? The calcium and oxygen. Calcium is plus 2, plus x is 0. X should be minus 2. It is calcium oxide. This is next compound. Plus 2 plus 2x is equal to 0. X comes out to be minus 1. Or oxygen minus 1 is peroxide, calcium peroxide. Plus 2 plus x is 0. X comes out to be minus 2, oxide. Plus 2 and x is 0. X comes out to be minus 2, again oxide. All these are oxides. This is oxide. This is oxide. Same way aluminium here is 3 positive. 3 positive into 2, 3 2s are 6 plus 3x is equal to 0. X comes out to be minus 2. It is aluminium oxide. It means oxides and peroxides of metals can be named. And here we have superoxides, only 3. KO2, RbO2 and CsO2. These 3 superoxides are going to have O2 1 negative ion, that is called a superoxide ion. Superoxide ion is O2 1 negative. O2 1 negative is odd electron species. It is 8 plus 1, 17 electron, or we can say odd electron species. When it is odd electron species, it's going to be paramagnetic. And due to paramagnetic characteristics, all these are colored, and their color is in reddish orange shade. Red orange shades are there in superoxides. The superoxides are generally reddish orange, paramagnetic, odd electron species is O2 1 negative, only 3 superoxides are known to you, and this question was there in your competitive exams. That question was, out of following, identify the colored species or paramagnetic species. When identification of paramagnetic species is there, so this question is having KO2 written in that, and KO2 is paramagnetic, that is a superoxide. Answer was KO2. Now this is about oxygen. Now some more point about oxygen. When we write oxide, it is going to be a diamagnetic ion. Oxide ion is diamagnetic. 6 plus 2, 8 electrons. It's a diamagnetic species. When we write O2 2 negative, it is peroxide. It is 8 plus 8 plus 2. 18 electrons are there. Again, it's going to be diamagnetic. So O2 2 negative is again diamagnetic. O2 negative is diamagnetic. And if we write O1 negative, so this is just hypothetical. O1 negative is not single oxygen with negative charge. This is not existing, not stable, not possible. Whenever we say O1 negative, it's hypothetical. Actual is oxygen, single bond oxygen, 1 negative charge, 1 negative charge, and this is named as O2 2 negative. And this is peroxide. Peroxide is not single oxygen with negative charge. It is 2 oxygens with 2 negative charge. Right? O2 2 negative ion is peroxide. And this linkage is named as peroxide linkage. This linkage is called peroxide linkage. The O2 2 negative peroxide linkage is there, and this peroxide linkage is present between 2 oxygen atoms. Same way, superoxide is not oxygen minus half. Superoxide is 2 oxygens with 1 negative charge. It's not single oxygen with minus half charge. Right? This is average charge which is coming to be minus half. It's not the actual charge on oxygen which is minus half. So this is all about your oxygen and oxidation states shown by oxygen. It means there is always a confusion. Oxygen can have which oxidation number? It can show -2, -1, 0, 1, 2, even plus half is also possible, and oxygen is having so many variations in oxidation state. Superoxides are possible only with alkali metals, group 1, potassium, rubidium and cesium. Only 3, right? Superoxides. Superoxides are always colored. They are paramagnetic. Reddish orange shade is there. Single oxygen with minus half is not given. It is 2 oxygens with -1. Right? 2 oxygens with -1. Same way peroxide. Peroxide is not 1 oxygen with -1 charge. It is 2 oxygen atoms with -2 charge. 2 oxygens -2, therefore 1 oxygen -1. That is about oxygen. Now we have oxidation number of an element can attain a maximum value and can also show some minimum value. And if we know the limit of an element to show maximum and minimum, so we can calculate oxidation number range. It means we must know that an element can show variable oxidation state. Variations are there, and this variation is from some minimum to maximum. If minimum to maximum is known to us, then our answer can be checked whether we are calculating correct or incorrect. Now we have the topic incorrect or correct check करने के लिए what we can do is we must know maximum and minimum oxidation number of an element. For this we have first group number 13. That is boron family. It is boron, aluminium, gallium, indium and thallium. Boron family can show maximum oxidation state of +3. Right? Out of these, boron is a non-metal. When bonded to metals, it may be -3. It means boron can show minimum -3 and maximum +3. Aluminium being metal stably show +3. Gallium +3 and +1, +3 and +1, +3 and +1. It means if in some compound we are calculating oxidation number and it comes out to be 5, you must be aware of, it's wrong. Boron cannot be +5, its maximum value is +3. Okay, so we must know the maximum limit of each family now. Next is carbon family, group number 14. Carbon, silicon, germanium, tin and lead. Maximum oxidation state possible for carbon family is +4. Then it is group number 15. Nitrogen family. Nitrogen, phosphorus, arsenic, antimony and bismuth. Maximum possible is +5. 16th group. It is oxygen, sulfur, selenium, tellurium and polonium. Maximum is +6 except oxygen, because oxygen can show maximum +2. Rest of the elements can have maximum number +6. Group number 17. It is chlorine, bromine, iodine and astatine. Fluorine we can't consider, it is only -1. Rest of the elements can show maximum +7. It means maximum limit of each family you must know. Now we learn this. Group 13 is going to be boron family. Maximum is +3. Carbon family maximum +4. Then we have oxygen family, nitrogen family first, sorry, +5. Oxygen family, it's going to be +6. Oxygen is the exception, leave that oxygen element, because oxygen maximum +2. Halogens we are having +7 except fluorine. So this is the maximum limit, maximum oxidation state possible for an element. Clear? I'll repeat. When we know the maximum oxidation state of an element, to answer more than maximum is not possible, will be known to us. Right? The maximum limit of each element we must know. Group 1 is always fixed +1. Group 2 is always fixed, group 2 +2. 13 group is +3, 14 is +4, 15 group is +5. 16 group except oxygen it is +6, 17 group it is +7 except fluorine. So these are the oxidation numbers. The next, in D block, we are having few elements. Their oxidation number, maximum and minimum, must be known to us. D block, scandium series. D block, and first we'll discuss scandium series. It is scandium, titanium, vanadium, chromium, iron, cobalt, nickel, copper, zinc. Maximum oxidation state of scandium is +3. Now learn it as +4, +5, it is maximum, +6, +7. It is group number 3. You must remember it as group number 3, maximum is +3. +4, 5, 6, 7. Iron +2, +3 and +6, and +6 in farads only. It is only in farads. Farads are FeO4 -2. X minus 8 is equal to -2 now. X comes out to be +6. Whenever there is a charge on that ion, that charge is written as equal to. For example, if it is neutral, we write it is equal to 0. When there is a charge, we write it is equal to the charge. The x minus 8 is equal to -2. X comes out to be +6. Cobalt +2, +3. Nickel +2, +3, +4. Copper only +1, +2. And zinc only +2. It means in D block, manganese here is showing +7 oxidation state. Osmium +8. This is the maximum oxidation number in periodic table. In periodic table, +8 is the maximum oxidation state shown by an element. The osmium +8. That is the only maximum possibility, +8. It means any element other than this, if coming to be +8, so your calculations are wrong. You have to be aware. You have to be just knowing the fact that +8 is possible only for osmium. Right? So this is D block and their oxidation state. You must remember scandium, titanium, vanadium, chromium and manganese. 3, 4, 5, 6, 7. These are the oxidation numbers, maximum limits shown by the elements. Right? Which element? It is again I write +3, +4 and osmium +8. Now let's calculate few oxidation numbers in some compounds. For example, if it is given KMnO4 and we want to calculate manganese. Now potassium is always a constant +1. Manganese is X -8 because oxygen -2 4 so -8 is equal to 0. X comes out to be +7. The question arises, why we have taken this oxygen to be -2? Oxygen can be -1, it can be -half also. Why we have taken -2 then? So you must remember 99% compounds are having oxygen with -2, oxide nature. Very few compounds are showing peroxides or superoxides. It means in general we prefer to go for -2, and if some anomalous behavior is shown, then we will correct it by some correction. Second compound, if it is given K2Cr2O7, K2MnO4, H2SO4, H2SO3, H3PO4, H3PO3, H3PO2, HNO3, HNO2, H2CO3, even HClO4, HClO3, HClO2 and HCl. Now we'll calculate oxidation number of these underlined species. We are going to calculate oxidation number of these underlined species. Calculate for potassium dichromate. I show you one calculation once again. It is plus 2 plus 1 into 2 plus 2x chromium minus 14 is equal to 0. 2x comes out to be 12. X is 6. It means chromium here is plus 6. Calculate K2MnO4 and further. Now let's calculate for K2MnO4, which is plus 1 into 2, that is potassium plus 1, 2 times plus 2. Plus manganese is X, minus 8 for oxygen, it is 0. Now X comes out to be 6. It means manganese here in first compound is plus 7, but in third compound it is plus 6. The variations are there in manganese. H2SO4, it is 2 plus X minus 8 is equal to 0. X comes out to be plus 6. H2SO3, 2 plus X minus 6 is equal to 0. X comes out to be plus 4. 3 plus X minus 8 is 0. X comes out to be 5. 3 plus X minus 6 is 0. X comes out to be 3. 3 plus X minus 4 is equal to 0. X comes out to be plus 1. 1. X minus 6 is 0. X comes out to be plus 5. 1 plus x minus 4 is 0. X is 3. 2 plus x minus 6 is 0. It means x comes out to be 4. Here chlorine, 1 plus x minus 8 is 0. Chlorine comes out to be plus 7, and we know that chlorine can be plus 7. It is maximum value for chlorine. 1 plus x minus 6 is 0. X comes out to be 5. 1 plus x minus 4 is 0. X comes out to be 3. 1 plus x minus 2 is 0. X comes out to be 1. Oxidation number for each element I just have shown how to calculate that oxidation number. These are simple molecules in which we can calculate oxidation number of underlined species, because hydrogen and oxygen, potassium and oxygen, these are known to us, and we can calculate the oxidation number of the middle one or the element other than these. So this is about oxidation number calculation. Now we have few species are to be learned by heart, and those are called radicals. If you know the charge of a radical, calculating oxidation number become very easy. For example, now we must know few radicals and then we can calculate oxidation number. Like sulfate, SO4 2 negative, carbonate, CO3 2 negative, nitrate, NO3 1 negative, sulfite, SO3 2 negative, sulfide, S2 negative. I'll repeat, this is sulfate, carbonate, nitrate, sulfite and sulfide. Sulfate, carbonate, nitrate, sulfite, sulfide. Now we have NO2 1 negative is called nitrite. ClO4 1 negative is called perchlorate. ClO3 negative is called chlorate. ClO3 negative is called chlorate. OH1 negative is hydroxide, you know very well. Cn negative is cyanide. SCN is 1 negative, thiocyanide. These are important ions, must be known to us whenever we want to know about oxidation number. Hydroxide, cyanide and thiocyanide. Right? How these will help us in calculating oxidation number? For example, if I write FeSO4 and my question is iron, so we must know that x minus 2 is 0, so x comes out to be plus 2, that's all. Because complete sulfate is minus 2, so iron should be plus 2. Same way we have anion oxalate, C2O4 2 negative. If I write CaC2O4 and calcium is to be calculated, so we must know that calcium is plus 2 and this oxalate is minus 2. C2O4 2 negative, oxalate is minus 2. If it is written chromium Cr2SO4 whole thrice, it means sulfate is minus 2 and chromium you want to calculate. It is 2x minus 6 is 0. X comes out to be plus 3. If it is written FeCN6 4 negative and oxidation number is to be calculated for iron. So we will write x minus 6 is equal to minus 4. X comes out to be plus 2. Look, charge is in front, we write x minus 6 and total charge should be minus 4. X comes out to be plus 2. If it is Fe, Cn thrice, SCN also thrice, and it is 3 negative. Calculate oxidation state of iron. Can you calculate oxidation state of iron? Yes, it is written as X cyanide minus 1, therefore minus 3, thiocyanide minus 1, again minus 3, it is equal to minus 3, X minus 6 is equal to minus 3, X comes out to be plus 3. Sometimes it is written as iron with carbon monoxide 5 times. So what is X or iron? We can say X carbon monoxide is neutral. So X comes out to be 0. If it is written PbNO3 whole twice. Nitrate, if is known to you, that's minus 1. The lead can be calculated. X minus 2 is 0. X comes out to be plus 2. Clear? So we can calculate oxidation number by using radicals also. It means if we know a group of species is bearing a charge and group of species is having a charge means a radical. And that radical, if is known to us, we can calculate the oxidation number of the other species attached to it. Right? HClO2, chlorine you have calculated. Can you calculate HBrO2 with bromine? If this is chloride time, this is bromide time. What is chloride now? ClO2 1 negative. And what is bromide? BrO2 1 negative. Right? So we can calculate oxidation number of bromine as 1 plus X minus 4 is 0. X comes out to be 3. So chloride and bromide both are having plus 3 oxidation state. This is how we can calculate oxidation number. Some rules are there, some set fixed oxidation states are there. If those things are learned to us, then we can calculate oxidation number of any of the species. Those rules, let's recap. We are having group 1, group 2. Group 1 always plus 1, group 2 always plus 2. Zinc plus 2, cadmium plus 2, aluminium plus 3 and fluorine minus 1. These elements are having fixed oxidation state, not changing at all. Next, hydrogen can be minus 1, it can be plus 1. When hydrogen is bonded to a metal, it becomes minus 1. And hydrogen is bonded to a non-metal, it becomes plus 1. Next, oxygen. Oxygen can vary from minus 2 to plus 2. When it is minus 2, it is called oxide. Minus 1 is peroxide. Minus half is superoxide. You must remember that oxygen minus 1, that is peroxide, is not a single oxygen atom. It is O2 minus 2. And superoxide is O2 minus 1. Not one oxygen with minus half charge. Charge is not divisible. It's a group of species with charge. O2 minus 1, that's why we are having one oxygen minus half. After that, we must remember maximum oxidation state of each group. For example, group number 13, it is plus 3, 14 plus 4, 15 plus 5, 16 group except oxygen, it is plus 6, and halogens, we are having except fluorine, rest all can be plus 7. D block, scandium, titanium, vanadium, chromium, manganese. 3, 4, 5, 6, 7. These are the oxidation number maximum limit. If maximum is known to you and if you are getting answer more than maximum, it means you have calculated something wrong. And that correction can be made by you. Few radicals we must know: sulfate 2 negative, nitrate 1 negative, carbonate 2 negative, etc. And with the help of those, we can calculate oxidation numbers. Whenever neutral species is there, like sulfur dioxide, and sulfur is to be calculated, and sulfate, sulfur is to be calculated. For neutral, you write it as x minus 4 is equal to 0. For ions, it is written as x minus 8 is equal to minus 2. If it is cation, NH4 1 positive, it is x plus 4 is equal to plus 1. Here x comes out to be plus 4. X comes out to be plus 6, x comes out to be 3, minus 3. So for charged species, sum total of all oxidation numbers should be equal to the charge on that ion. For neutral, it should be equal to 0. That's all about your oxidation number calculation. We can calculate oxidation number of species given to you in the compound. That's all for the today's class. Thank you, and you can recap this knowledge. That's all. Thank you.